Good afternoon, everybody. We're going to go ahead and get started since it's just turned 2. My name is Caitlin Armendariz-Shergill, and I'm the Manager of Outreach and Engagement for the University of Arizona Health Sciences. I'm happy to welcome you all to the first session of Tech Talk Tuesdays for the Spring 21 semester. Tech Talk Tuesdays is a series of bi-weekly conversations all about engaging thought leaders, experts, researchers, and healthcare professionals in conversations around the advancement of technology and health sciences. We're happy to have Dr. Michael Grandner today from the Arizona College of Medicine. He's going to be presenting sleep health technology, apps, wearables, Nearables, big data, and the future of sleep tech. Just a quick note, today's presentation will be recorded and posted on the University of Arizona Health Sciences YouTube channel. I'll send out a link to everybody who registered for the talk via Zoom. And then after today's presentation, we'll open up at the end for questions. You're welcome to submit those via chat and I'll go ahead and ask them on your behalf. Or at the end, you can just jump in and ask them yourselves. And with that, I'll turn the time over to Dr. Grandner.
Hi, thank you. I've turned off my video to save bandwidth, so I apologize for that. But thank you for inviting me to speak today on this really important topic. As always, I have too many slides, so I'm going to try and go through as much as I can. First, a little bit about me. I'm a clinical psychologist by training. I'm the director of the Sleep and Health Research Program here, as well as the Behavioral Sleep Medicine clinical program. And my primary appointment's in the Department of Psychiatry, but I do work in a number of different departments. And my interest in sleep health technology goes back to some of my graduate training where I got to work with some of the people who really founded this field. And I've sort of grown with it since. And when I came up with the title for this, I thought, like, what would be the best thing to talk about? So apparently, looking at the title I chose everything, but I'll try and fit it all in. Not everything will get the attention it deserves. This will mostly serve as a broad overview. And on here, while I'm talking, you can see contact information for me. If you ever want to reach out, if you have any questions, I'm happy to help. First, I do want to make a note. I do have a couple of disclosures. I have gotten grants from some industry partners, and I have done some consulting, though none of the work I've done with any of that is going to find its way into this presentation at all. So this is totally independent of that, but I just wanted to make sure I disclose that. So I want to start with the big picture here. Sleep is a non-negotiable universal biological need. In that context, yet we live in a society that often sees sleep as an unproductive use of time, and nothing is worse than unproductive time. So this has led to societal pressures that devalue sleep. And so we get ideas like this one. At the same time, we have this reawakening to the importance of sleep health, where we're increasingly recognizing how important sleep health is for our wellness, for our well-being, for our mental health, and other aspects of health. So if sleep is so important, how do we measure it? The traditional approach is with polysomnography, and polysomnography is great, but at the end of the day, it's based on technology from the 1930s and 40s. And determination of sleep is largely based on brain electrical activity with information from eye movements and muscle activity, and it's done in a laboratory. And polysomnography is great. It's the gold standard for a reason, not because it's gold, but because it's the best that we have. So why do we need wearables if we have such a good measurement in polysomnography? Well, this is why. Most people don't sleep in a lab on a regular basis. And even if they did, their sleep would be fundamentally different from what would be seen at home. Also, in-lab assessments don't account for things like night-to-night variability or daily or weekly rhythms. So that's where wearables sort of came to be. The first devices used to estimate sleep-wake outside of a laboratory were built on the foundation of movement transducers developed in the 1960s and 70s, actually. The aim of this was to study individuals, at first hospitalized psych patients, but eventually everyone else, in regular day-to-day activities in order to determine movement patterns. Over time, this thinking evolved and expanded into an interest in understanding rest activity rhythms in free living individuals. The foundation of a lot of this relies on something called piezoelectricity that I'm only going to talk about very briefly. Piezoelectricity refers to the electric charge present in certain solid materials. It gets its name from electricity due to pressure. It naturally occurs in various types of crystals and can be manufactured in certain forms of ceramics. And this becomes important in terms of measuring movement. You'll see how. So this is an illustration of piezoelectricity where you compress a mass and it changes its voltage. So the originators of accelerometry were these original movement transducers from the 1970s. For example, an EEG spring wire was soldered to a metal weight attached to a piezoelectric element or a ball in an electromagnetically charged tube. It measured raw voltage change with little precision. It was mostly just movement counts. So this is like the progenitors of sort of modern day sleep tracking. Then came accelerometers. So these devices were a major advance over motion transducers. It allowed for greater precision, not only whether movement just occurred or not within a time frame, but how much movement. So here's a gross oversimplification of how an accelerometer works. So you have this mass. As you accelerate upward in the image, gravity and inertia is forcing the mass down to compress this piezoelectric material, which then results in the change in voltage. And then this spring can quantify the degree of movement that the mass underwent. So this is an oversimplified version of how an accelerometer works. But at the end of the day, and you'll see in a sec, even modern accelerometers that you see in smartphones, for example, are still essentially based on this same principle. You have a mass, you have piezoelectric material, you have voltage output, and you have movement compressing it. The next major advance was this idea of multiaxial accelerometry. As you could probably get from that image, you can only move in one direction, and most people don't only move in one direction. So you create this idea of multiaxial accelerometry. So the way you address this is you put multiple accelerometers at orthogonal angles from each other so that you can measure movement in multiple directions and multiple kinds of movement. And then you come up with algorithms and strategies for integrating these multiple signals into a single output. Triaxial accelerometry really is just 3 accelerometers placed at right angles to each other. So whatever direction you're moving in, it'll capture one of them. But again, more modern accelerometers might have more of these. So where we've moved to is this idea of MEMS. These are micro electromechanical systems, just micro small, electro because they're changing voltage, mechanical because they're moving systems. So many current accelerometers use these MEMS chips. This is about the size of one. This is a nanotechnology application to accelerometers. They're extremely sensitive, very small. So here's a schematic of one. And you can see here, they still have, even though they're microscopic, you still have the same principles of measuring the movement of a mass changing with acceleration to produce a change in voltage. Still to this day, like this is the foundation of how all these things work. The first major review on actigraphy for sleep was published in 1995. And this was the data, and here are the studies that were published. If you look at sleep-wake agreement with polysomnography, you'll see these numbers are quite high. This includes studies before there was any kind of algorithm and automated scoring, even some original hand scoring. But you can see from back into the 70s and 80s into the early 90s, these studies that came out already had relatively high agreement with polysomnography. Over the next 10 years, you had a number of studies coming out establishing validity and really establishing actigraphy, this movement-based measurement trying to quantify sleep versus wake. This is just a bunch of the studies that have come out. There were even more on different devices, showing, again, generally good agreement here. One of the more recent studies that I think was the largest that was ever done was the Marino-Buxton validation of ActiWatches. So ActiWatch being one of the devices that you see on the market a lot in research, again, using wrist-based accelerometry for estimating sleep versus wake. So what exactly all the algorithms are and exactly how they measure it, I couldn't fit that in this talk, but if you have questions, just let me know. What they tested these devices across 90 people, found that, first of all, they found clock synchronization was a problem. So I think that's important to note when you're looking at these devices, that you want to make sure that you know what it is you're looking at. There were some group differences that were not significant. Overall accuracy was about 85% for men and a little higher for women. In terms of estimating timing, it was about 86 to 87% effective, whether it was measuring daytime or nighttime sleep. And in terms of looking at insomnia patients versus good sleepers, it was still pretty good, though less effective for insomnia patients. Again, there's a whole rabbit hole of why insomnia is an issue with actigraphy, especially if you're laying in bed for a long time not moving, but it's still pretty useful. So I think this represents the best of the studies that was done to sort of wrap our heads around the evolution of technology from the late 60s, early 70s into the 90s and 2000s, which was mostly just stuck with wrist-based movement transduction and more advanced into accelerometry, but that's where it was. So here's some problems with some devices right now. Most well-established devices are now kind of somewhat outdated. They haven't innovated much in the last decade or two, which is good if you're running a study so you know exactly what you're working with. But at the same time, there's a lot of innovation in the field that hasn't really made its way into the lab. Many frequently used devices are not well validated. So some of the newer devices that have some impressive technology, people are using them, but they haven't been well validated, unlike some of the older devices. Many newer devices use different scoring approaches and algorithms that are not standardized. Sorry, the picture cut over this. And many newer devices are adding other signals into sleep-wake detection. So I'm going to talk about that a little bit. And as information increases, questions arise as to what to do with this information. So where we are now in terms of actigraphy and research, here are the guidelines for the Society of Behavioral Sleep Medicine. You can look these up. It involves technical specs, patient instructions and other information, how to identify invalid entries, which happens a lot, and scoring of nighttime and daytime sleep, and reports and interpretation. So there's lots of information here in these guidelines. Another more recent guidelines document, this is an international consensus document about wearable sensors for sleep. This is about if you're developing technology for sleep and you want to be able to say your device is a wearable that measures sleep, what does that mean? And what tests do you need to subject it to be able to realistically say that? So things like comparison against polysomnography, what sort of stats would you use? You want to look for bias, you want to look at Bland-Altman plots, things like that. So if you're, for anyone interested in how technology needs to be assessed, this guideline document is for you. So for the rest of this talk, I'm going to focus on what I see are sort of the current and future issues with sleep technology. And some of these, again, I apologize, I'm only going to be talking about very briefly. Each one of these bullet points could be a whole talk, but I'm really just trying to give a landscape here. So first one, advances in actigraphy, so moving beyond some of the traditional metrics. Beyond actigraphy, adding heart rate data to movement, as a lot of the newer devices are. Sleep apps, promises and promise. the approach of Nearables, looking to the future, innovations in sleep technology. I'm going to talk a little bit about leveraging big data for understanding sleep health. I'm going to talk very briefly about machine learning and artificial intelligence. It's mostly just there to remind you that this is coming, this is going to be a big thing, and I'll just talk about it very briefly. And then a little bit on bedroom behavior, promoting sleep health. So in this world of technology and assessment, where this talk is mostly focused on sleep assessment technology, there is a role in modifying sleep behavior. So current issues with actigraphy as it is. So optimizing accuracy is still a goal. Dealing with sleep disturbances, especially certain things that actigraphs tend to be good at picking up, but also certain things that they tend not to be good at picking up. Complex signal processing, I'll mention an example, show you an example of that, and integration with other signals. So here's some data from the Merino paper showing that in general, and this is something that you should take in mind for any kind of sleep tracking device. They tend to be highly sensitive, and the problem is with specificity, so not sensitivity. So for people who are unfamiliar, sensitivity is, if you have a test that's sensitive, if the thing is present, it will find it. If it's specific, it will only find it if it's there. So if you have high sensitivity, you'll have a lot of true positives, but you might have a lot of false positives because you're very sensitive. You'll see it a lot. If you have low specificity, it means you might miss some. So you want to balance sensitivity and specificity. So for example, if something's really high stakes, so something like a pregnancy test, you want it to be very sensitive. You don't want to have a false negative. So you want high sensitivity, but you also want good specificity too. You don't want to, think it's positive, but actually being negative. So like COVID tests right now, this issue of sensitivity and specificity. Some of the tests are very specific where you're not going to get false positives, but you might miss some true positives. So those tests are less sensitive. So anyway, sensitivity, specificity. This is important for sleep too, because most people, if they're measuring their sleep in bed, most of the time they're in bed, they're actually asleep. So healthy sleep efficiency is about 90%, which means most of the time, when someone goes to bed, at least 90% of the time they're in bed, they're actually asleep, which means that by default, if you're going to guess if someone is in bed and you want to guess whether they're awake or asleep, and if you guess sleep 100% of the time, you're actually correct 90% of the time. So that's why sensitivity is actually easier in these devices, because if you overscore sleep, you're more sensitive, but you're more likely to be correct statistically. So the trick is finding complicated sleep problems and specificity. And so here's some data that shows that the more wakefulness you have during the night, the more the device is going to under-detect that wakefulness. It's going to assume sleep more than it should, the more you're awake during the night. And then just another, on an unrelated note, talking about signal processing, here's some data from Till Renneberg's lab where they're saying, is there anything else we can get out of this actigraphy signal? Can we estimate anything about sleep staging or depth of sleep? Usually the answer is no, but they're starting to dig into the signal to try and look what they're calling lids, but it's more about looking at if they can detect micro level movements and clusters of movements that might give you some indication of sleep depth. So just saying that there is some advancing going on. So instead of just focusing on reproducing sleep estimations achieved by other indirect measurements, so why are we using actigraphy just to potentially replace brainwave detection? Those are two different measurements of things that get at sleep. Rather than just try and replace other types of measurements, what other measurements of sleep can we get in the actigraphy signal that maybe we even can't get anywhere? I think this is a really important question for the field. Let's see here. Next, I think another important question for the field is, how do we leverage the ability of this device to capture sleep-wake behavior in free living conditions that isn't easily recalled by self-report? Because, outside the laboratory, one of the only really good ways to measure sleep is with a diary. A diary is still the best way to capture insomnia because there are things in insomnia that we don't even seem to have the technology to even be able to measure. So what if there are things in these wearables that we can pick up that even in-lab polysomnography can't? Because again, that's not even very good for insomnia either. And then how can we better validate the in-bed analysis window when all the validation studies are in the lab? So by definition, these validation studies are in the lab when you already know they're in bed. And so the algorithms are all about detecting sleep versus wake when you know they're in a sleep opportunity. Much trickier is figuring out when someone's in bed or when they're just sitting on the couch. And those algorithms are not really well established. And that's why in scientific studies, we always have to tweak these windows. It's really important. I'm going to spend a little time on this issue of adding heart rate to actigraphy, because a lot of the more modern devices are using this. So how does this work? Heart rate signals at the wrist are obtained through something called photoplethysmography, or PPG. So here's an image of a PPG signal at a finger, but it's a similar principle. What you have is you have a light source and then you have a photodetector, and you're measuring the reflection of the light essentially off the blood vessel. And what you get is some of the light gets absorbed and some of the light gets reflected back. And the changes in how the light gets reflected back should be indicating, the pulse through the blood vessel, where everything else should essentially be constant. So these PPG signals are quite accurate for obtaining heart rate data. Here's an example of, I'm getting a little ahead of myself, but here's an example of two different well-known commercial devices, an Apple Watch and Fitbit devices, and showing that relative to a gold standard heart rate detection, just measuring these at the wrist are pretty darn accurate. And they might fluctuate by only a few percent from the gold standard. So heart rate and sleep. So, okay, we got this PPG signal. It does reflect heart rate pretty well. Why the heck is it useful for sleep? Well, heart rate and heart rate variability vary across sleep and across the day and across sleep stages in a systematic way. So you can see changes in sleep versus wake based on your heart rate, which is the top image as an example of a paper that looked at heart rate across 24 hours. And the bottom image is a different paper looking at heart rate variability. So you can use heart rate and heart rate variability. And the way they do this for estimating sleep is, first they acquire the raw data, then they remove noise, especially movement-based noise that you get out of this heart rate data to try and get it to be clean. Then they separate it into epochs, just like with sleep, usually 30 seconds. Then they extract features out of it, depending on the device and the software. You get beats per minute from the heart rate, but you also can potentially get QRS, at waves and heart rate variability, et cetera, depending on what you can pull out. Then they process, weight, and reduce the dimensions so they can get a single determination. And then they use classification algorithms, which are usually derived from sort of machine learning and other complex processing techniques on these extracted features to estimate, okay, what can we use about this data to figure out whether you're awake or asleep and what sleep stage you're in. So tracking back some of the initial development. So one of the earliest examples I found was this paper from Redmond and Connor Hennihan using cardiorespiratory signals to approximate EEG-based sleep scoring. And they showed moderate classification accuracy versus EEG, and this was in sleep apnea patients. So this is the list of all the different factors they extracted out of the cardiorespiratory signal that they used to try and estimate sleep staging. Another relatively early version of this was the WatchPat device, which used a different peripheral cardiorespiratory signal to try and estimate at least REM versus non-REM. And you could see even in 10 years ago, they were relatively good ballpark estimates of REM versus non-REM here. So more modern devices. So this is the Fitbit device. For this study, I think it might have been the Charge 2 at the time, but actually the technology around the sleep staging is essentially the same across devices. But you can see this paper from Beatty shows that not only is there a really good agreement, wake versus sleep, but you also have relatively good prediction of sleep stages. And when I say relatively good, I mean absolutely nothing like in-lab. This is not a replacement for in-lab sleep staging. It's not, so that you can see the levels of accuracy here are not a replacement for in-lab polysomnographic sleep staging. They're sort of a rough ballpark, but they are still a rough ballpark. And you can see, and you can get that there is some degree of accuracy here. But another thing that's worth pointing out is the sleep-wake detection might actually be better than movement alone when you're adding the heart rate data. Another device that's commonly used is the Oura Ring. So here's another validation study that shows that, you know, the sleep-wake agreement is actually quite good. The sleep staging is also not terrible. It's probably, you know, it's probably useful as a ballpark, but again, it's not very precise. But again, you're using peripheral at the finger or at the wrist measure of heart rate, and you're using that to guess what sleep stage the outer layers of your cortex are in at any given 30-second window. The fact that it's even that close, I think is pretty amazing, but we shouldn't be overinterpreting that. So there's surprisingly little, I think, out there on Apple Watch, but the best paper that I've seen is the one from Walsh and colleagues, where they actually derived the algorithm themselves out of the raw data. They used raw data output from movement, they used the heart rate, and they used a clock proxy to estimate circadian pressure. And they showed a pretty good estimation of sleep versus wake and moderate accuracy for REM versus non-REM, just like everything else. All these devices seem to be mostly in line with each other. So on the left, you can see what happens when you add the signals. Heart rate only is an okay, but not really good estimation of sleep versus wake. Motion only is pretty good, but when you combine them, you know, you get maybe marginally better. And then in terms of measuring sleep stages, heart rate alone, again, is not very useful. Movement alone can sort of be useful a little bit, but then when you combine them, you actually get some pretty good information. This is a paper that just came out that compared multiple devices. Here you have the ActiWatch, which is sort of a gold standard laboratory-based device. And then you have other devices on here. You have the, hold on just a second. So you have the ActiWatch on here showing pretty, again, good sensitivity across the board. You'll see that the problems are mostly in terms of specificity. Then you have the overall accuracy, which is sort of minute-to-minute agreement. Again, it's going to be high if you have generally good sleepers anyway. But what you can see here is you have ActiWatch, you have the Headband, which is also movement only. Then you have the Fitbit and two different Garmin devices that are using movement and heart rate, presumably. And what you can see here is the accuracy is pretty comparable. You actually have relatively comparable specificity, though these other devices don't seem to be quite as good, but they don't have the same sort of validation data behind them as, say, Fitbit and Fatigue Science do, and especially not ActiWatch. So, but I think this is an important question where, like, if as a scientific community, we've come to accept the strengths and limitations of an ActiWatch for measuring sleep, wake behavior, and free living conditions, you really can't say that some of these other devices, especially this one, whether it's the Fatigue Science device or the Fitbit device, you can't really say that they're not quite as good. These devices are direct comparisons showing that it's at least in the same ballpark. And even the Garmin devices, the overall accuracy was still quite good, even with the lower specificity. When you're looking at sleep staging compared to polysomnography, again, you have overall accuracy issues where they're not they're not a replacement for in-lab polysomnography, but you can see in some of these devices, it is a relatively decent ballpark in terms of their ability to distinguish sleep staging compared with polysomnography. So it's again, it's not a replacement for in-lab, but it is a pretty useful ballpark. A little bit about apps. There are a lot of apps for sleep, white noise apps, calming music, sound-based stuff, sound recorders to pick up snoring, sleep coaching apps, which is a totally different topic and I'm going to get into today, and sleep tracking apps that use the device accelerometer and ones that use other functions of the device. The accelerometry-based apps are among the most downloaded sleep apps. Instructions are usually to place the device on the mattress or under the pillow to detect movement. Sometimes these apps attempt to schedule an optimal rise time based on when the app guesses that an individual is ready to wake up. Most of these claims are not founded or based on actual data. The one app that probably has the best evidence is the Sleep Cycle app. So here's the citation for that validation study. It's probably the most well-known, but still, compared to polysomnography, it underestimated light sleep by 54%, overestimated deep sleep by 28%, and overestimated sleep latency by 135%. It overall showed reasonable 86% accuracy for sleep-wake detection, though this was somewhat a function of normal sleep. It only really correctly identified 50% of wake epochs. Overall, about 46% accurate in estimating sleep stages. And under normal sleep conditions, it could be a reasonable estimate. But again, it's sort of a rough ballpark. I'm going to talk very briefly about Nearables. So this is devices that are not wearables. They're near you and measuring their sleep. So one is the Sleep Score Max, or sort of the successor to the ResMed S Plus. So there's a couple of different papers validating these, basically using radio frequency technology or RF technology to assess respiration and heart rate and movement, and using that to guess at sleep-wake parameters. So this is a device, you don't even have to wear it, and it's at your bedside, and it could estimate aspects of sleep. Another relatively newer device is using radar technology. This is one called Somnify. This paper was recently published, showing again, relatively good data. It'd be interesting to see where this goes compared to sort of gold standard. So that there's a future in these Nearables. So here's an example of an UnderBed sensor. This is something you put under your bed. So here is a paper that essentially showed that this device was okay at measuring sleep versus wake, and not quite as good for sleep stages, but maybe they're getting there. In terms of, and here's another UnderBed sensor device that had a published validation study. This one didn't look quite as good as some of the others. It showed more errors, but it might have to do with how it was tested. But again, you have these UnderBed sensors. Here's some more data from that paper that just came out looking at these Nearables versus polysomnography, showing overall pretty good accuracy, high sensitivity, and moderate level specificity, which seems relatively on par with either the scientific grade devices or the Fitbit device or the fatigue science device too. They're all sort of in the same ballpark. In terms of sleep stages, again, similar ballpark. You have okay ability to sense sleep stages, at least get a general sense of what's going on. I should note, though, that although this isn't replacing in-lab polysomnography, what you do have in these devices that you never can get in lab is days and days and potentially weeks and maybe even months of data in a single individual. So you can look at change in sleep staging across time potentially. So what do we even do with those data is an important question. Then there are devices that are headband devices that you can wear. So here's a sleep profiler, which is pretty good data to support it. So it's not the same, again, as an in-lab sleep detection, but it's sort of a different mode of assessment than sort of wrist-based movement and heart rate. It is using brainwave-based technology where it's just reduced. Here's another one, the Dream Headband, also similarly looks like it performs quite well, especially for measuring sleep in the home. Where are all these things going in the future? So there's a whole ecosystem of sensors out there that can address aspects of sleep and variables related to sleep. So this comes from a paper that wasn't really sleep focused, but if you're interested in things like depression or anxiety or insomnia or poor sleep, you have these behavioral markers, you have other features, and there's all kinds of sensors that can pick up these features. And so in the future, hopefully we'll get a better sense of how to integrate all these sensors together. And so here's a couple of ideas that I've seen in the literature that I think are neat. One is, instead of actigraphy, there's tapography, which is when you wake up and you pull out your phone, what's the first thing you do? You're tapping on your phone. So here what they did is they used touches on the phone to approximate wake versus sleep activity, because people are on their phones all day. And they actually showed, and you could see it's messy, but you could still get ballpark data. So even if you have no sleep tracking data at all, and all you do is say have some big data database of when people are touching their phones, you actually might get a pretty good sense of what people's sleep-wake behavior is like. Here's another one. Instead of a Nearable, here's a Hearable, where they actually put the device in the ear, where they can get EEG-based data out of the ear, which shows relatively good agreement with potentially other head-based assessments. So again, as a future direction, maybe we can just put a fancy earplug in somebody and get another dimension of sleep-wake estimation. Then, now you have these smarter beds that are being built. So you have a couple here that are either using difference in pressure sensors and temperature control and other approaches to try and get people better sleep where they're sleeping. I couldn't find a lot of data on these, though hopefully some of these manufacturers will start funding some research soon, so we can actually get some published data, so I can see the degree to which these are actually helpful and maybe refine them. But the bed is where we sleep. So what can we do? What can we learn about building better beds based on sleep science? And some of this has to do with heating and cooling. This is another big push. So here's a few different devices that are using heating and what we're learning about temperature regulation, heating and cooling to maybe improve sleep. So you have a device that's a wearable that can help people regulate temperature. There's one there's the thing you put on your forehead. There's a device that's validated for improving insomnia. And then you have like blankets and mattress covers from other companies that what they're doing is they're helping to help people regulate their temperature at night. And so there's all kinds of new technology out there. Maybe in the future we'll have sleep-friendly smart homes. So you have these smart home systems where you have these sensors around the house, and then you can use information from those sensors to better engineer sleep environments and even interface with other aspects of the home. I do briefly want to talk about these commercial sleep devices. They've been on the market for about 10 years now. There was a quick uptake and tremendous innovation, but there was a problem of limited validation that we're starting to get over. A lot of the industry was really, really slow to embrace the idea that actually they need validation or people are not going to buy into what they're doing. There's also this idea of measurement versus intervention, where just measuring something doesn't necessarily mean you're going to change it. But I have a whole slide on that, so I'm not going to talk too much. But then there's a lot of disillusionment and frustration. This is one of my favorite images about this, where you have this technology trigger, which creates a massive uptake in visibility. And then you get what they called the peak of inflated expectations, which I think we were at a few years ago. And then there was the trough of disillusionment, which I don't think we're still in. I think we were in maybe a year or two ago. But now I think we're coming up the slope of enlightenment, where we're starting to learn from the lessons of the last bunch of years to try and see how do we leverage what we know about sleep science, translate it into technology, and that actually helps people in a scientifically valid way. So maybe there's some renewed interest. Very briefly about big data. There's lots of different ways to leverage big data for sleep. You have public health surveillance systems, medical record systems, databases from devices, assessments, user data. You can get summary data versus granular data, and you can link data across different different uses. You could do all kinds of stuff with it. And especially if you're integrating multiple data streams, whether it's wearables, health records, genetic data, device use data, and app use data, especially as there are whole platforms being built just to leverage this connection to help provide better, more useful information. And then there's all kinds of other stuff you can do. So this was a great study using big data to look at sleep. This was Microsoft looking at people typing in the Bing search engine and what their keystroke speed was across 24 hours, showing dips in things like alertness and performance. Another excellent example of big data and sleep is the UK Biobank, which is measuring tens of thousands of people, at least up to over 100,000 people with actigraphy, and hundreds of thousands of people in terms of sleep screening. And so here's an example of a paper that came out of that, where they're looking at, based on the sensor technology that they're wearing in these tens and maybe over 100,000 people, how do people spend their day? And where's sleep in there? So I think this is really, there's all kinds of UK Biobank data coming out. So this is super interesting. And that takes you into machine learning and AI. As the data get big enough, there's all kinds of stuff we could be doing. So there's also the difference between AI, which is where a program learns and adjusts, to machine learning, which is where the program can learn from data without relying on the rules programmed into it, where it can help figure out the rules. And then what you have now is this idea of deep learning, where you have these supervised, and now you have this unsupervised learning where the program can, in essence, essentially figure out even what the rules are. So as you get these bigger and more complicated data sets, there's all kinds of new things we can learn. So using wearables, they're easy to use. They tend to be low cost. You can get useful information. But there are some limitations, especially in terms of validation, if you have these devices on the market that you don't know what it is they're actually measuring. And people also then get confused about what to do with that information. So just because you have information doesn't mean you need to do with it. So the real problem is, as technology as intervention, is you have, for example, like a really complicated bathroom scale, but at the end of the day, it's just a bathroom scale. Like a bathroom scale is not a weight loss program. And a lot of technology solutions to sleep issues have focused on measurement and quantification, not necessarily figuring out what to do with that data, whether it's a machine learning, deep learning, AI sort of approach of how to get better insights. But then as a psychologist, as a behavior person, like I want to end with this idea of there's all kinds of things we can do with this data to help people improve their sleep-related behaviors. And a device that just measures things is just a bathroom scale. When people get old, people get tired of those. Those get old very quickly, especially when the numbers don't change. So if we can help people change, if we can help people use that information better, and again, that's a whole other area, but I would challenge everyone to think about sleep technology as more than just measurement. So thank you very much. I know I went a little over, but there's a lot of ground to cover and I didn't cover it even enough. But a quick plug to the lab. Here's all our students. And I appreciate our funders for our research. And thank you very much. Here's my contact information, my Twitter handle. If you have any questions, if there's anything I brought up that you want to talk about more, definitely feel free to reach out. So now I'm going to stop share and I'm going to turn on my video.
Thank you so much for your presentation, Dr. Grandner. If anybody has any questions, feel free to jump in. If you'd like to submit them via the chat, I can also ask them for you.
Okay. There's one question in the chat while people are preparing questions, and it's about sleep stages. And it's an excellent question. So what they're asking is, how important do you think sleep stages are in trying to differentiate good from poor sleep? And this is really important, especially as this idea of sleep stages is getting out of the sleep lab and into the world, and people are looking at their devices. So on the one hand, yes, REM sleep is important. Deep sleep is important. They're important for the brain. They're important for the body. But worrying about your makeup of sleep stages, I liken that to worrying about the content, the gas content of the air you're breathing, where it's like, if I came to a doctor worried about, am I breathing in enough oxygen? So equivalent to, am I getting enough deep sleep? Am I getting enough REM sleep or whatever? And I would go to the doctor, I say, am I breathing in enough oxygen? The doctor would say, well, is there anything wrong with your lungs? That why you would think there would be a problem? No. Okay. Well, is your air really polluted? Maybe your lungs are fine, but the air is polluted and you're not getting enough oxygen. Well, no, the air's not polluted. Like, well, and your O2 sat is fine, you're probably fine. And it's the same way with sleep stages, where it's like the equivalent to the lung problem is, do you have a medical condition that's preventing you from getting into REM sleep or deep sleep, or are you taking a medication that's blocking it or something? Is there a barrier in the way? Can we identify what that barrier is? If you have one, let's treat it. And then the equivalent to the environment and the pollution would be, is there something in your environment that's keeping you up during the night? Or is there something around you that's keeping your sleep shallow? Well, if there is, let's fix that. The exact makeup of the sleep stages themselves, I wouldn't necessarily worry about. But it can get people thinking about the importance of sleep. You just don't want to overinterpret it, especially now that the data aren't super precise yet anyway. Okay, so I'm in the chat here. If anyone...
The first one we got was could you comment about using a wearable device with a CPAP machine?
Yeah, so I mean, CPAP machines are used for sleep apnea to help keep the airway open during the night. And a wearable, so historically, a lot of sleep wearables are not great for sleep apnea because people with sleep apnea, especially if it's undertreated, will move around more, or they'll have more abnormal sleep during the night, and it shows up as sort of worse sleep, but it's hard to know whether it's a sleep issue or just the breathing issues. But still, especially if you're being treated, a wearable could probably be really useful to get a sense of what's going on. A lot of people with sleep apnea use their CPAP and still feel like their sleep quality isn't good. Well, the wearable might be a great window into seeing what's going on, to see like, okay, well, maybe you still have a lot of sleep fragmentation, or maybe the chronic pain you have is interfering, or diabetes, or maybe there's just a lot of noise in the environment and that's keeping sleep shallow. So yeah, I mean, if you want a window into what's happening, that's good. I mean, also don't forget sleep diaries too. I mean, you can get information from those as well. Any other questions jump out from you in the chat? I'll let you come through.
Yes, so the next one we got is, what are your thoughts on orthosomnia?
Yeah, orthosomnia is a term developed by Kelly Barron, where to describe this idea of people who are so overly into their quantification of their sleep that they lose the forest for the trees, where they're trying to micromanage aspects of their biology that they really don't have that much control over, so they get all freaked out about it. These are the people who are saying, I only got 17 minutes of deep sleep, but I need at least 90 or whatever. That's an anxiety issue, where it's like, it's a clinical issue in that they're trying too hard, and they're stressing over things that actually they don't have control over. I mean, usually our problem is we're trying to convince people that sleep is important. But in orthosomnia, these are people who are trying to use wearables to optimize and make things perfect, and you can take things too far.
Another question we got in the chat is, do you think current sleep doctors need more data from the patient, such as sleep-wake cycles over several months, to make a more accurate diagnosis?
Yes and no. The yes part of the answer is, I think there's information here that will inform how we understand how sleep progresses over time and how sleep disorders are treated over time. The problem is those data don't exist yet. Those studies haven't been done yet. So most sleep physicians or other sleep professionals, honestly, a lot of them have no idea what to do with some of these data. Some of us do because we're used to them, but to be honest, a lot don't, but that's okay. I think for most of sleep medicine, at least how it's treated now, those data don't really come into the conversation as much because people don't know what to do with them. But if you're using a wearable and it's sending you the message that something's wrong with your sleep, go to a sleep specialist. They may not look at your data from your wearable. They might not know what to make of it, but they'll know what questions to ask to figure out if you have a sleep disorder. They'll know what tests to run to figure out if you need treatment for a sleep disorder, or what medications to give, or what other treatments to use, or whatever. And then you could track those outcomes with your wearable and sometimes see benefit there. So even if your doc doesn't know what to do with those data yet, because honestly, the field is just learning, it's still useful because it got you in the door. And then you can let them take over from there.
Excellent. So another great question we got is, let me just scroll back for just a second, is have we done a good enough job defining normal sleep to know if we're measuring the right things? It appears that we formulate a lot of our sleep science based on pathologic conditions like sleep apnea, rather than understanding how sleep contributes to health.
Yeah, that's my soapbox. That what does normal even mean to begin with? Like, does normal mean normative, which means where most people are? But it's sort of like, what is normal weight when 3/4 of the population is overweight? So is that normative? Does it mean optimal? In which case, how do you define optimal? We don't have a test for optimal sleep. We don't know what is optimal sleep yet. We're still trying to figure that out. So I would define normal sleep as free of diagnosable sleep disorders, where people fall asleep within a reasonable amount of time, probably with 20 minutes or less, spend probably on average 20 minutes or less awake during the night, sleep in 1, 2, or 2 chunks plus a nap, wake up feeling feeling fine or maybe a little sleepy, but the sleep inertia wears off. Don't have trouble staying awake during the day in general. If don't fall asleep right away because they're sleep deprived. Like, I think if right now, normal is sort of when you eliminate all of the problems, what are you left with? But I think it's an important question of what is normal versus optimal versus normative. And at the end of the day, most of what we have is our experience. And if we're fine, then it's probably fine. The other thing to remember is, every human, since before humans, has slept every day of their entire life, pretty much, give or take a few all-nighters. Evolution figured this out a long time ago. You don't have to have perfect sleep to have perfectly good sleep. And this goes for all the orthosomnia people too. It's like your diet doesn't have to be perfect to be perfectly fine. And so I wouldn't worry about micromanaging sleep so much as, if you've got a problem, let's try and figure out what it is and fix it. If you don't have a problem, you're probably okay.
Excellent. Another great one we got. I think we have time probably for one more question.
Okay.
What can you say about measuring sleep patterns in operational environments in non-clinical populations, especially sleep that's divided between night sleep and daytime naps, often away from the home?
Excellent question. This is a huge issue, especially in our society. We've got shift workers. We have, so this idea of operational environments is, like, to me, that means on the job. So it could be transportation workers behind the wheel. It could be factory workers at the machines. It could be office workers sitting in front of their desks. It could be doctors and nurses taking care of patients. It could be athletes training and performing on the field. I mean, it could be military, among the whole wide range of jobs there are there too. I mean, sleep plays a role in performance at probably most levels, whether it's mental performance or physical performance. And anytime you're in a situation where either physical or mental performance is important, sleep is probably important. So I think wearables have a huge potential for not only quantifying and giving feedback to people to help get their sleep better, but that might help provide information like, if you're a truck driver, and you're on the road, when do you pull over? Or, like, do you start this next trip? Or if you're an athlete, when should you be training, based on when your competition is? Or if you're a doctor, when do you need to hand off a patient? Like, there are all these questions that we could use sleep and fatigue and circadian research to help optimize and make better. And at the end of the day, it makes people safer. It could hopefully improve people's quality of life, and improve our productivity. I mean, so I didn't put this in here, but we've got data that shows that a lot of people sacrifice sleep for more work, because they think they're being more productive. But the data actually show that you're wasting time and you're less productive. You would be better spent putting a little more time to your sleep, and then you'll be more productive the next day, get more done. Instead of seeing sleep as a cost of time, if you start seeing sleep as an investment of time in your next day's productivity, you'll do better. And that's where, and I guess maybe that's a good place to end, because that's a great opportunity for bringing the sensors technology with the wearables and field and maybe environmental and decision making and machine learning technology in with the behavioral science too, to help use what we know to help everybody out and make all our lives easier if we can.
Thank you so much, Dr. Grandner, and thank you so much for your talk today, and thank you everybody for attending. That's all the time we have for questions now. I encourage you, though, if you still have questions that were unanswered, Dr. Grandner provided his email as well as his Twitter handle, so please feel free to reach out. And as well, there was a recording of this session. It should be posted on a few days to the University of Arizona Health Sciences YouTube page. However, I will be sending out a link to everybody that registered as well. So keep an eye out that in your inbox for a few days. Thank you.
Thank you very much. All right, thank you.